discussing it. We have, at this point in time, argued a force is conservative, by definition, if it is a negative gradient of some potential function. We showed that that's the same thing as saying, as independent, the work done by that force is independent of the path traveled. We showed also that that in turn is the same as saying the force will do no work when we take it along any closed loop in space. And if we take the system along any closed loop where all the particles in the system move from where they start along some trajectory back to where they start, a conservative force does no work. So we've showed this. We've shown this. We need to show one last thing. If I give you some force, is it conservative? This is yes. This is no. This is what is smoking. We can't tell very easily at this point. We don't yet have a simple test. When we're given a force, we can't yet quickly determine conservative or it's not conservative. There is a way that we have got, and that is to try and work out the work done from A to B by this force, and to ask, is that work independent of the path? And if it is, it's conservative. If it isn't, it's not. That's one way to actually compute the potential if it exists. You run into trouble if it doesn't. But there is another way. And it's based on something called Stokes' theorem. Who here has heard of Stokes' theorem? Right. So Stokes' theorem says that if I take some closed loop in space, for some surface, and that's what it is, then the integral around the boundary of that surface, which is some closed loop, right, of some function, some vector function, dot dr is equal to the surface integral over the surface of the curl of it in the normal way. Right. That's Stokes' theorem. Suppose I should say. And why am I writing it down on the board? Because the surface is normally bounded by some closed loop. Why do I care about those loops? Why do I care about closed loops? We talked about closed loops. Why do I care? If I can calculate the work done by the force on some closed loop, and I get an answer of 0, and if and only if I get an answer of 0, that force is conservative. Okay. Okay. So, if for some closed loop in space, I can find some surface of which that closed loop is a boundary, right? Then I can use Stokes' theorem. I can say my closed loop that I found in space is a boundary of the surface, and as a result, the integral of f dot dr, or the work done on a closed loop by the force, right, is equal to the work done by the surface that is enclosed by this integral over the surface enclosed by that closed loop. Okay. All right. And if the value is 0, if it is conservative, the value is 0. What does that mean? If I want this integral to be 0, for any closed loop, the thing inside had better be 0 as well. I can always find a closed loop small enough so that the value of this thing, if it was not 0 anywhere, I can find a closed loop small enough so that it's all positive in that region or all negative. And if that was the case, this would never be 0. Okay, try to reason that to yourself. The point that we want to get at is that if we can write the closed loop is the boundary of some surface, then if we can do that for any closed loop, then for any closed loop, this being 0 means this had better be 0 everywhere. Right. So we seem to have another condition for conservatism. There's some caveats here that we have to consider. First is the following. Be cautious about the one assumption that I made here, which was that I give you a closed loop and you can find a surface around that closed loop. That's not always true. It's not always true. I call a set or a domain or a region in space simply connected if it is true that for any closed loop in that region, there is a surface for which that closed loop is a boundary. That's when I call a domain simply connected. When the domain is simply connected, all of this logic follows through. So when the domain on which my force is defined, the domain on which my force is defined is a simply connected domain, then it is true that this condition will tell me that the force is conservative. What about the converse? If the force is conservative, what's the curl of the force? Well, if the force is conservative, then F is equal to minus grad U. So the curl of F is equal to minus the curl of grad U. What's the curl of a gradient? 0. Always 0. That's a tough problem today. Prove that. Not hard. So the curl is 0. So if the force is conservative, then the curl is 0. If the curl is 0 and the force is defined in a simply connected domain, then bam, 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 it's conservative. Just be very careful. If the domain is not simply connected, we cannot say that it is conservative or that it is not conservative. We have no inference. If the domain is not simply connected, we cannot say anything about the nature of the force when we are given this. Right. So, but if this is not 0, at any point, then we know that it's not conservative. If this is 0, then it is conservative if it's simply connected, and if it's not simply connected, we cannot tell. Right, so that's all the little intricacies of this theorem, which you can hammer out and flatten out by just going through all this logic. I don't want to sit here and bore you with too many technical details. The technical details will be supplied in the notes, and you can peruse them at your leisure. So we have now basically defined everything we need to know about forces. In the tutorial, we'll consider a couple of interesting ones, and you'll come across a case where it's not simply connected, and you'll have to ask, is it conservative anyway? But for now, let's leave it there. we now have a whole bunch of things that we can do to test whether a force is conservative, to reason about conservative forces. If beforehand I know that my domain is simply connected, then the following statements are equivalent. Curl of f is 0. F is conservative. F is path independent. Work done on a closed loop is 0. All equivalent. You say one, you mean all the others. If it's not simply connected, you simply cannot complete one of the implies. Right. So that's our full array of power now with regards to conservative forces. That's what we're going to need to use, our toolkit, if you like, when we're dealing with conservative forces and deriving potential for those forces. Let's see how we find a potential once we know that a force is conservative. So let's look at gravity. Right. So I am in three-dimensional space, and I want to find potential. That's the force of gravity. 0 in the x direction, 0 in the y direction, and minus mg in the z direction. It's got no dependence on x, y, and z. It's uniform everywhere. We want to show that this is a conservative force. How do we show that? We work out the curl. Okay, it's defined where? In all of space. Is all of space simply connected? Sure it is. Give me any loop, closed loop in all of space, and I can find a surface connecting it. Right? There's no holes or funny things that I have to avoid. All of space is simply connected. If I give you a 2D space, for instance, if you give me any loop in 2D space, there's a surface. Any loop, there's a surface. Any loop, there's a surface. So it's simply connected, and we can use this theorem. Curl f is 0 implies f is conservative. Out of interest, what's not simply connected? Let's take a plane and let's put a hole in it. Let's say that nothing inside this hole is inside my set. Now some force defined on this region, can I take any closed loop and find a surface completely contained in the region between it? No. If I choose a closed loop here, I'm in trouble. The surface between here is there's a hole in it. Right? I cannot collapse. Another condition that you can think of is, can I continuously collapse any closed loop to a point? And I certainly can't. If I took that, I treated it like a rubber band, and I tried to collapse it, it would get stuck in the hole. Right. So 3D space with no exclusions or anything is fully connected. I can use this, and I can say f is conservative. Let's compute the potential function. Out of what did we say was the potential function? We said u of x, y, and z is defined to be minus the work done in going from some reference point, which I'll conveniently choose to be 0, but you can choose it to be anywhere, to your point, x, y, z, which I'll call P. Right. That's how we define it and we derive these things. So all we have to work out is what this value is. Well, this is minus the integral along any path, because it's path independent, along any path from 0 to my point of f dot dr. So we can compute this by doing the path integral along any path of our choice, our choosing. So let's, for instance, draw our 3D plane, x, y, z, and let's take a point in that 3D plane. Point here, say, give an idea where it is, I'll draw this side. And let's take a path to that point from 0. I'm going to choose this path to begin with. Path that starts here, goes along the x-axis, gets to the x coordinate of the point, goes along the y-axis, gets to the x and y coordinate of the point, goes along the z-axis, and gets to the z coordinate of the point. Right? That's a path in space from 0 to the point. I can certainly choose that path, there's no problem with that. So let me now evaluate the integral. How do I evaluate the integral of f dot dr along this path? Well, I have to parameterize each little region of the path as a line and perform the line integral. So this one goes from 0, 0, 0 to x 0, 0. This one goes from x 0, 0 to x, y, 0. And this one goes from x, y, 0 to x, y, z. So it's 3 segments that I'm going to be integrating my force along. And by the way, you can do this kind of thing for any force. I'm doing it for gravity, which is a particularly easy example, but in the tutorial there will be others. More difficult ones, different ones, that you can do the exact same thing, right? This path is a path that you can always choose, or you can choose another path, it doesn't matter. Right, so let's evaluate this. This is minus the first line. For the first line, I can parameterize the first line as r of t is equal to t comma naught, where t goes from 0 to x. Right? Is that okay with you guys? I have 0, 0, 0, 0.0001, 0, 0, and so on and so forth. And I move along the path until I'm at x, 0, 0. Right. So I'm integrating from 0 to x. Let's not use t, let's use s. It's a parameter. T, everyone confuses with time. It's not cool. Right, so let's see what it is. S, 0, 0. So it'll be f of x, 0, 0. F evaluated at that value. Dot r prime t dt. What's r prime? The derivative of r with respect to s is just 1, 0. Yeah. Plus. Now let's do this one. This one, how will we parameterize it? Are we going from x, 0, 0 to x, y, 0? So what are we doing? X, something, 0, where something goes from 0 to y. That's easy enough. My parameterization is x, s, 0, where s now goes from 0 to y. Right? Square brackets is irrelevant, right? We only consider the integrals. So the point here is, well, let's take the derivative since we'll need it. R prime, no, f, is it that point? Right. So the first one will be x1 naught. Oh no, it's naught 1. We're going to get x to the constant, right? Naught 1. So what do we get? Oh boy, we're running out of space. Well, we get an integral from 0 to y of f of 0s0, right? Dot 0, 1, 0. Now I'm going to start erasing stuff. We now want to do this part. Well, it's pretty simple what this one's going to be. R of t is going to be starting from xy0 to xyz. R of s is going to be x, y, s, and s is going to go from 0 to z. Right, so The third term here is going to be plus integral from 0 to z s of 0, 0, s dot 1 yes. Okay. We haven't yet said anything about f. We've just said careful here. This one is x. No one said it was right, so I mean x, y, s, right? That's what R of s is. F of R of s, we have to put that. Okay. So let's simplify this. If we think of f as fx, fy, and fz, right? Then f dot 1, 0, 0 is just fx. Right? And f dot 0, 1, 0 is just fy. Right? And f dot 0, 0, 1 is just fz. So we can write this out in a very simple fashion. Maybe I should go write this out very quickly as minus, right, the first one will now look like integral from 0 to x of fx at x 0, 0 dx plus integral from 0 to y of fy of x 0 ds plus integral from 0 to z of fz of xys ds. Okay. So going along that path, everything is great. We've now got an expression. We haven't yet even used f. We've done this all generally so far. Now let's substitute in. Let's use f. F is what? 0, 0, and minus mg, right? It's not even dependent on x, y, or z. It's the same everywhere. So evaluating it here, evaluating it here, and evaluating it here will give the exact same results in this case, right? This is equal to minus, okay, what's fx? What's fx? 0, right? So integral from 0 to x of 0 dx plus integral from 0 to y. What's fy? 0. Y plus integral from 0 to z. Oh, what's xz? Minus mg. Yes. Okay. So this is equal to minus of this integral is 0, this integral is 0, and this integral is minus mg s evaluated between 0 and z minus mg z. Let's cancel the two minuses and we get, which we know in love. Minus this is equal to mgz, the gravitational potential energy. Right. Now we could use the same path, that blue path, to work out the potential of any other function, not necessarily this one that we have. We do the same thing, only now fx and fy might not be 0, and then maybe x's and y's and the integrals, z. We have to just be a bit careful. We chose a reference point here. We chose the point 0 as our reference point, and we integrated from 0 to our point. If the force was ill-defined at 0, if for instance it was divided by x squared plus y squared plus z squared, we could no longer start from 0, we'd have to integrate from somewhere else. Right? But no matter what we do, we can integrate along any path from our chosen reference point to my final point, and we'll get an expression for the potential energy. Is the potential energy unique? This is yes. This is no. Are there any, what are you smoking people this time? Right, so potential energy is not unique. Those people who are brave are correct. It is not unique because I could have started at any reference point, right? So long as I'm consistent about what reference point I start at, I don't have to start at 0. I can start at any other point, right? And what you can find, and you can try this, is if we started instead of at 0, 0, 0, if we started at x0, y0, z0, then we would have gotten, instead gotten u of x, y, z is equal to mg z minus z0. Right. You can do that integral from x0, y0, z0 instead of from 0, 0, 0 as an exercise. Does this matter? The answer is no. We only care about the gravitational or any potential energy because we're going to take its grad. We're going to differentiate it. When you differentiate something, what happens to arbitrary constants? Bye-bye. Out the door. So this expression is just mgz minus mgz0. This term here is a constant. It doesn't matter. It can be eliminated because in terms of physical content, what's actually going to happen when we get the force, it's going to disappear when we differentiate. Right. The reason why we might like that constant is because it might mean something physically to me. Would I prefer to measure the gravitational potential from the floor or from the center of the Earth? Well, for my purposes, I think the floor is very good, thank you very much. So the floor is my, my Z0, and I may want to measure my height here from the floor rather than from the center of the Earth. So really it's a matter of preference where you measure your potential energy from, so long as it increases as you go up and decreases as you come down. So that's pretty simple. Everything works out fine. We went along that path. Just in order to rub in the point that these things are path independent, and also because sometimes that path won't be good enough, let's work out the same thing. We're going to take the potential. But this time, let's just go straight. I'm choosing another path. I'm perfectly at liberty to do this. So I'm going to use one path, one segment that goes straight from the origin to point x, y, z. And let's see what happens when I work out the gravitational potential energy by using this path. Alright, well it shouldn't be very different to what it was before. I just need to parameterize the path. What's my parameterization of the path now? I need an arbitrary equation for a line connecting 2 points. Well, not so hard. I can just call it xx, yx, zx. S goes from 0 to 1. Okay? Let's check that. When s is 0, what's this value? 0, 0, 0. We're over here. When s is 1, what's this value? X, y, z. We're over here. So this path, the straight line path, from here to here on the green line, is given by this parameterization. Xs, yx, zx. Right. So, what is the value of the integral when we go along this path? Well, it's not too hard. We just do it. Any issues with that today?